Multivariable Calculus section 14.2, line integrals. And actually, they should really be called curve integrals, as you will see. Review of integration along the x-axis. For example, if we have a function and we want to find the area under the curve, we integrate along the x-axis, and basically what we're doing is adding up infinitely many infinitely thin rectangles, or you could think of it almost as adding up infinitely many line segments attached to and along the x-axis. And so we get an integral from a to b of f of x dx, which adds up infinitely many line segment lengths f of x values times the instantaneous changes dx along the x-axis. Now line integrals are a little different. Instead of integrating along the straight x-axis, we're going to integrate along a curve. And that's why they really should be called curve integrals. And so what we're doing is we're adding up infinitely many infinitely thin line segments along the curve. So you're adding up the length of the function values times the instantaneous changes along the curve, not the instantaneous changes along the x-axis. And so the line integral along C of any function of 3 variables or less or more, ds, adds up infinitely many line segment lengths, that's your f values, times the instantaneous changes ds along the curve C. So here's another picture from a different text. There's a curve on the xy plane, and then the function values are the z values. And so we're finding out a sort of curvy area along this curve C. The line integral along the curve C of f of xy ds adds up infinitely many line segment lengths f of xy values times the instantaneous changes ds along the curve C. And so this is when the curve is in 2 dimensions. Surface area example. We've actually already done a line integral, sort of, but it wasn't called that. Back in the section of single variable calculus, we took a curve and rotated it around the x-axis. And then in order to compute the surface area, basically what we did was we added up all the circumferences times the instantaneous changes along the curve. If f of xy gives the circumference of the surface of the rotation, represented by C at each of its points on the xy plane, then the line integral f of xy ds computes the surface area, and in the picture shown, f of xy would be 2 pi r, or in this case 2 pi y, and that would be your function. Here's a real-world example. Let's say we have a wire of variable density bent the way this curve is shown. If f of xyz gives the density of the wire represented by curve C at each of its points in 3 space, then the line integral along the curve of the function, which is the density function, along the curve ds, so we're multiplying by instantaneous changes along the curve, that will compute the mass of the wire. That's about as real world as I'm going to get in this lesson. Okay, so let's look at the parameterization of a curve in 2 dimensions. So we have a timeline, we used to think about this as time, where we parameterize a curve by assigning to x and y a function of t. So this is a picture of how that works in 2 dimensions. And then in 3 dimensions, it's the same idea. We have a timeline, but this time we need 3 functions, one for x, one for y, and one for z. And yet we still manage to express this curve then in terms of a single variable t. And we can also think of that as a vector function, where r of t is the vector that points from the origin to the same point, and so the components of the vector function are the same as the parametric functions for x, y, and z. Now we have to talk about different kinds of curves. So here's a smooth curve which means there are no breaks, cusps, or corners. So basically it's differentiable at every point. And then here we have some curves that are not smooth. A curve defined by a vector function, a parametric vector function, is smooth if the derivative vector function is continuous and never equal to the null vector. If you have it equal to the null vector, it's possible to get a cusp. Now this curve is called a piecewise smooth curve. You'll notice that if we broke it into 3 pieces, each of the 3 individual pieces would be smooth. So this is called a piecewise smooth curve. A curve defined by a vector-valued function in T is piecewise smooth if it consists of a finite number of smooth curves joined end to end. So it's not discontinuous if it's piecewise smooth. Okay, so line integrals with respect to arc length are as follows. Given C is a smooth curve, the line integral f of x, y, z ds can be evaluated by converting to parametric form. In fact, that's the only way I know of to actually evaluate it. And how do we do that? Well, we go from t1 to t2. We convert x, y, and z into their various functions. And then ds is the formula for the length along the curve dt, which you have actually seen before. So that is what you have to use for ds, the change along the curve. Okay, so let's just take a look. Let's review where this ds is coming from. Derivation of ds. Here we have a space curve, and we can connect points on the space curve with straight line segments, and then each of those line segments has a length, which I'll call d for distance sub k, and we find that length very easily just using the distance formula. So you're taking the change in x squared, the change in y squared, plus a change in z squared under the square root. So each of those little green line segments has a length like this associated with it. So if we add up all the instantaneous changes with an integral, we can approximate that by adding up the discrete changes delta s, each of which is numerically equal to d sub k. And then as the number of segments goes to infinity and the lengths go to instantaneous changes, then the integral along the curve would be the square root of the instantaneous changes in x, y, and z squared under the square root. Now this looks kind of funky, so we have a little trick we pull. We multiply by 1, well, a special form of 1, dt over dt, and we take that bottom denominator dt and put it inside the square root by squaring it, and so we get our familiar formula. So this is the integral along the curve, the line integral along the curve C of just ds, and normally we would have a function in front of that, but here the function of x, y, and z is just 1, so the integral will actually return the length of the curve. So it would be as though we're adding up 1 all the way, infinitely many little lines, infinitely thin line segments of length 1 all the way along the curve. And so that would be equivalent numerically to the length of the curve. Line integrals with respect to coordinate variables. You have 3 of those in 3D. And the difference is that we integrate along the x-axis, or we integrate along the y-axis, or we integrate along the z-axis. And so we're looking at the changes along the x, y, and z-axis, but since we're parameterized, the change along the x-axis is the derivative of x times dt. And so that's why you have that extra x prime, y prime, and z prime rather than the square root, which is the length, the change along the length of the curve. Now the 3 integrals above typically occur together, and so what we do is we have the 3 changes separated, where p, q, and r are the individual functions of x, y, and z, And so what we can do here is take the x function times the change in x plus the q function times the change in y plus the r function times the change in z, and separate those into three separate integrals. Now, it disturbed me a little bit that on the left there were no parentheses. So I thought there should be parentheses, but the book assured me that it's acceptable notation to leave out the parentheses, that expression is thought of as one complete entity, and therefore you don't need the parentheses. Properties of line integrals. Line integrals with respect to arc length give the same result regardless of the orientation of the curve C. So in other words, if we start at one end and go to the other end, or if we reverse that and start at the different end and go to the first end, we get the same value for the sum of all those little infinitely thin line segments, which kind of makes sense because you're just adding up positive values, lengths along the curve. It doesn't matter what direction you go in. However, line integrals with respect to the coordinates give opposite results when the orientation of the curve C is reversed, because now you're going in the opposite direction for dx, dy, and dz, and so you get a negative value if you switch the orientation of the curve and start at the other end. So now we'll move on a little bit and talk about line integrals with respect to vector fields, specifically a force field. So let's say we have F as a force field and curve C in that same field, in the same space as the field, and R of t is a vector valued function with non-zero continuous derivative v of t, which is r prime of t, which to take the derivative of a vector valued function, you take the derivative of the individual components. Now, that means that non-zero continuous derivative just means it's a smooth curve, and so everything's going to work nicely. So we have a vector field, and we have a curve drawn in that field. Now, if we take the velocity vector and compute its length, then t would be the unit tangent vector, because the velocity vector is tangent to curve C, and so t now then is 1 unit long, and that's our unit vector tangent to the curve. So this is all like preliminary notation and to get you back familiar with vectors. Now work, remember, is usually a force times distance is the idea behind work. So the work done by the force field to move a particle along the curve is given in two ways. The second way is actually a little simpler to me, but you can use whichever one you prefer. So if you take the force and dot it with the unit tangent to the curve, and then move that along the curve ds, all the little changes along the curve, that's the same as if you dot the force field with the changes in r. It amounts to the same thing. And r then is just the changes in x in the I direction, the changes in y along the j direction, plus the changes in the z direction along k. So you can think of F as the force, and then dr are all the little distances added up together. And so you're still doing force times distance, but now you're using vectors. So now we have a theorem that will make the computation easier. Given vector field F equals pi plus qj plus rk with continuous component functions, and t the unit tangent vector to a smooth curve C, then in fact we don't have to reinvent the wheel each time with a difficult integral. We can just use this simpler integral on the right, where p, q, and r are the functions in x, y, and z. And then what we're going to do is, since that's a single integral, we have to somehow change it so that we have a single variable. And so what we do is we just change p, q, r, and the dx, dy, dz in terms of t, so that everything gets in terms of t, and then we can integrate it very easily. Now, why is this 2? Well, it's quite simple. We have f dot tds equal to f dot dr, and f is just pqr, and dr is just the changes along the axes, and so when you dot those together, you get what we have written there above. So now we're going to do some problems. Number 2, evaluate each of the following 3 line integrals given this function and this parameterization of x and y. And here are the 3 line integrals they want. The first one is going to take more calculation. So here's the formula with respect to t, and we don't need the z components because this is just a 2D example. And in our case, the function is x, and then the square root uses the derivatives. Derivative of x with respect to t is 1, and the derivative of y with respect to t is 2t. So those are the values we square. And then this is a simple u substitution problem, and we get the integral 1/8 from 1 to 5 u to the 1/2 du, which integrates to 1/8 times 2/3 u to the 3/2. Evaluate it from 1 to 5, and don't forget to change your limits of integration if you do a substitution. And that comes out to 1/12 5√5 minus 1. Now the second one is the line integral along the x-axis with respect to the x-coordinate, and so our function is still x, and dx, you have to take the derivative of x with respect to t, which is 1 dt, and that integrates to a 1/2 t squared, evaluated from 0 to 1, and so we get a 1/2. And finally, the line integral with respect to the y-axis, or the y-coordinate, we get the same function but times dy, and y is t squared, so dy is 2t dt, and that integrates to 2/3 t cubed from 0 to 1, and that value then is 2/3. Number 4, evaluate each of the following 3 line integrals given f of xy equal 2x minus y, and this parameterization of x and y. And so it's the same 3 line integrals as before. Here's our formula with no z component because we're in 2D here. And so we have our function 2x minus y and our derivatives, cosine and negative sine respectively, and then that square root simplifies nicely to 1, and x becomes sine t and y becomes cosine t, and then we have our limits going from 0 to pi over 2 as given, and that's an easy antiderivative, and when we evaluate it we get 1. Now the line integral with respect to the x-coordinate, same function, dx then is the derivative of sine t, which is cosine t dt, and 2x becomes 2 sine t and y becomes cosine t, and to integrate that we have to distribute the cosine and then use a couple of identities, the same ones we used back in single variable calculus, and I didn't bother showing that integral by hand. I'm sure you could do it. The final answer is 4 minus pi divided by 4. And then the last one is very similar. Our function is still 2x minus y. We substitute for x and y, and then dy is the derivative of y equal cosine t, so that becomes negative sine t dt. And again, you would multiply that out and use identities if you wanted to evaluate this by hand. The final answer comes out to 1 minus pi over 2. Number 8, evaluate this line integral given p equals y root x and q equals x root x, and c is the curve defined by y squared equals x cubed from 1, 1 to 4, 8. So here's the curve they're talking about. If you solve for y, you get y equals plus or minus the square root of x cubed, but we're in the first quadrant, so it's just the positive. And this time they did not give you the parameterization. You have to figure that out. So we're going to use this line integral, and filling that in with p and q, we get these 2 integrals. And there are many ways to parameterize it. There are probably a lot more clever ways of doing it than I did, but I just did it an easy way. I let x equal t, and y then, if you solve above, you get y equal t to the 3/2, because y equals x to the 3/2. And then that means that t just goes from 1 to 4, the same as x. So here are our 2 integrals in terms of t. Notice that y is t to the 3/2, and then root x is t to the 1/2, and then dx is 1 dt. And then in the second integral, x is still t, and root x is t to the 1/2, and dy then is the derivative of y equal t to the 3/2, which is 3/2 t to the 1/2 dt. Now if you combine those are both t to the squared if you combine all the t's, and so because they have the same limits of integration and the same dt, we can combine that into one integral, and we get 5/2 t squared, which integrates to 5/6 t cubed, evaluated from 1 to 4, which gives us 105/2. And notice that's a very big answer, well, because we're integrating along a curve that's obviously greater than 7 units long, and the values that we're integrating are big too. So it's not really a surprise that we get a rather large answer for some of these line integrals. Number 12, evaluate this line integral given the vector field defined by that function, and see the line segment connecting these 2 points. So in this case, the curve is a straight line. Hence, line integral makes a little more sense. Now notice we're going from the first point to the second point, and so the change in x is 2, the change in y is 3, and the change in z is -4, because z is going down from 3 down to -1, which is 4 units. And so the parameterization is pretty straightforward. It's just a line. X starts at 2 and then has a change of 2, so we've got 2 plus 2t, and then y starts at -1, has a change of 3, so that's -1 plus 3t, and z starts at 3 and has a change of -4, so that's going to be 3 minus 4t. And this is the line integral we're going to use to evaluate. F dot TDS is much more difficult, so we use the easier line integral that's equivalent. And so here's our line integral in terms of p, q, and r. And then we have to change into t. Now what I did was I combined them ahead of time, because each of the dx, dy, dz is going to have a dt in it. And so I just factored that out ahead of time. And dx is going to be 2 dt, and dy is going to be 3 dt, and dz is going to be -4 dt. So I just put those numbers in the front, and then we have y times z in those parentheses, and x times z in the second set of parentheses, and x times y in the third set of parentheses. Now you have to multiply that all out and collect like terms very carefully, and it comes out, I didn't show all the steps, but it comes out to that integral. And so then now it's the hard part's over. That's very easy to integrate. And so we integrate that integrand and evaluate from 1 to 0, and that gives us an answer of -2. Number 18, evaluate this line integral given this function in 3 variables, and see the elliptical helix determined by these parametric equations. Okay, so here's a picture of the elliptical helix, not to scale. And notice that that's a very long curve, and so we can expect a rather large answer for our line integral. Here's our formula. This is not a force field problem. It's just a line integral. We're adding up infinitely many, infinitely thin line segments along the curve. And this is the parametric form. So we're back to the formula from the previous problems. So in our case, t goes from 0 to 5 pi over 2. The function is x times y, so that ends up being 4 cosine t times 9 sine t. And the derivatives of x, y, and z, respectively, are -4 sine t, +9 cosine t, and 7. And so if we square those, we get what we show there under the radicand. Now, Dr. Bill says, good luck with that. And actually, it is doable, but we'll just skip that and go straight to the calculator. So typing it in very carefully, we get an answer of approximately 176.895. I told you the answer would be big. So let's review parameterizing C. Remember that the curve C must be parameterized by a single variable, usually t, in order to provide an integrand for our single integral. C can be expressed either as a vector function, r of t, or as 3 separate parametric equations, x equal f1 of t, y equal f2 of t, etc. We use these same parametric functions to rewrite the x, y, and z in our vector valued function f to change f of x, y, z into f of t. So everything in a line integral must be expressed in terms of that one variable, which we usually just use a t for the heck of it. You can use any letter you want, but t is popular. All right, so what if the parameterization is not provided? You're not given a vector that spells out that traces out the curve, and you're not given parametric equations. You're just given some kind of description of C. Well, in other words, no R of t is provided to describe C. Then you have to create a parameterization, and any valid parameterization will give the same final answer, but there will be some that are easier to use than others. Some common parameterizations include linear and circular. So let's take a look at some that you will probably want to use. Here's a linear example. Let's say C is a line segment from this point to this other point. Well, let's take a look. Now you got lots of choices here, but I'm seeing that x goes from 1 to 2. So I'm just going to let x equal t, and then I'm going to let t go from 1 to 2. Now conveniently in this particular example, I notice that y is just twice x, and therefore y can be parameterized by 2t. Now z is a little trickier because it goes from 7 down to 4, so I want it to go down 3 units. But I also want it to start at 7. So if I go down 3 units and I want my starting point to be 7 when t is 1, remember I'm going to let t go from 1 to 2, then what do I need to add? Did you say 10? Yep, 10. And then of course you have to write down what the parameters are for t, because those are going to be your limits of integration. Now you could have done it a different way. You could have let t go from 0 to 1, and then x would have been t plus 1, etc., etc. And you just have to use your noodle to figure that out. Okay, second example, circular example. Let's say C is the ellipse defined by this equation. Well, that's supposed to remind you of this famous Pythagorean identity. But what we need to do is get a 36 in front of the two terms on the left so that we can factor the 36 out and have our identity. So what we really need is 36 sine squared t plus 36 cosine squared t equals 36 to mimic this ellipse. And so what do we need x to equal? And what do we need y to equal? Did you say y equal 2 sine t? Because then you get 4 times 9. And x equal 3 cosine t? Because then you get 36 cosine. Now you could have done the other way around. You could let x equal 3 sine and y equal 2 cosine, but generally we like to let x be cosine and y be sine, but either way it works. Okay, so those are the two common parameterizations that are going to come up a lot, and there may be other esoteric ones that you just have to figure out on your own. Woohoo! What is this thing? Well, this is the clever way that you draw an epihypocycloid. Epihypocycloid, I think that's how you say it. So if you want to go out and make one of these out of cardboard so you can draw this thing, knock yourself out. Woohoo!